Okay, let's just finish up this chapter with the solution to this projectile motion problem. Remember, we had a soccer ball that was kicked from the ground at an angle of 40 degrees above the horizontal at an initial speed of 22 meters per second. And we want to know how long it takes in time to come back down and hit the field, measured from the kick time, and how far does it go horizontally as measured along that flat field. Okay, so following the suggestion here, which is a good idea for all these kinds of problems. First, we want to draw a diagram so that we can put our axes on it and be clear about what the initial and final are. So it seems reasonably simple to place the kick at the origin. You don't have to choose that, but there's really no motivation to make any other choices. And we don't have to choose plus y is up. We could have chosen it down, but why not choose plus y is up? That means ay is going to be minus 9.8, and we'll take plus x to be in the direction that the ball is traveling horizontally as it leaves and comes back to the field. And so in that case, x0 and y0 would be 0. That sort of simplifies things, and our final x is going to be a positive number. Second, we need to, so I guess I didn't say here, but we're going to take initial to be just after the kick, right after it leaves the person's foot, and final to be just before hitting the field. And in that case, the acceleration of the ball is constant, both the x and y components, all the way through there. Ax will be 0, Ay 9.8 in between initial and final. Because we're asked information about the final, the state that I'm calling final, so there's not too much choice there. All right, we are actually given enough information to pretty easily compute Vx0 and Vy0 here, although we're not given them directly. We're given the angle and the speed of the kick. So we can draw a little diagram. Here's my 22 meters per second. I should have labeled it here, but this angle is 40 degrees right in there. And what we want in order to use the kinematics equation is the x component of the initial velocity vector and the y component of the initial velocity vector. And what we're given is the hypotenuse of this triangle and this angle down here. So we can use our knowledge of trigonometry or properties of right triangles to say that, well, how do I get from 22 meters per second to the Vx0 side? I'm going to pivot through the angle that's given there, the 40-degree angle. And I like pivoting through the angle. I like cosine better than sine, so I'm going to multiply that 22 times the cosine of 40 degrees to get this horizontal one. And similarly, to get from here to this side, I'm going to have to pivot across the angle that's given right there. And that would involve a sine. And so we can calculate both initial x and y velocity components. And they're 16.85 meters per second for x, 14.14 for y. And now I can use those to help solve kinematics. So what are we given? We're given x0 and y0. They're both 0. Ax is 0. Ay is minus 9.8. Y final is also 0. If I'm calling this right before it hits final, it's gotten back down to the field. And what we want is the time it takes between initial and final and how far it goes horizontally. That's our x final. Some, in some books they actually put a little f after the x, but I think Giancarlo doesn't, so I'm trying to follow him here. Okay, so let's look at the choices we have here. We want the time it takes and we want the distance it goes. How might we approach this? Well, in order to find the time it takes, we know, I guess looking at this now, I'm approaching the x part first. If we wanted to find x, we could look at this equation right here and say, if I only knew t, I already know ax, I already know vx0, I already know x0. If we only knew t, we could find x, and we want to find t, so it looks like we're going to have to find t first, and then we can simply plug into this circled equation and find x. And in order to find t, we can use the y versus t. What do we know here? We know y final is 0, y initial is 0, vy0 we just calculated as some positive number, and ay is minus 9.8. So the only unknown in this equation I've circled here is t. So we can use it to solve for t. So let's start with the y one. We'll get t, that's part of our answer, and then we'll go back to the x equation to get the other part of the answer. All right, plugging in, y final is 0, it's back at the field. Y initial is 0, it starts on the field, right? And we just calculated Vy 0 and Ay is minus 9.8 in our coordinate system. And we get something that, you might be disappointed and say, it's a quadratic equation. I really got to use the quadratic formula. Even, if you're an expert at the quadratic formula, it's kind of a pain to plug it in your calculator and think about it. I really don't want to do that. That's actually not true in this case. This is a quadratic equation, but we don't have to use the quadratic formula because there's no constant term over here. The constant term is 0. So ax squared plus bx plus c equals 0. That c is 0 in this case. And that means we can just solve this by factoring. What I can do is, there's a common factor of t in both of these terms. So let's factor out a t in front. T times 14.14 gives this term, and t times this minus 1/2 times 9.8 times t gives this term, the second term. Strangely enough, it appears that I'm missing a plus sign right there. So there actually, it looks like, should be a plus sign in between the t and the 1/2. Okay, now you've probably heard this long ago, and some of you may be familiar and some not, but when you have a product of two algebraic expressions equaling 0, you can't have both of them be non-zero. In other words, when you say, I multiplied these two things together and I get 0, the only way for that to happen is for one of them to be 0 or the other one to be 0. If you take two non-zero numbers and you multiply them, the result's going to be non-zero. So if they multiply together to give 0, that means either the first one is 0, first factor is t, so either t equals 0, or this thing in parentheses is equal to 0. And of course, we knew we were looking for the solution y equals 0. Well, of course, at t equals 0, it was at y equals 0. That's not the solution we're looking for. We're looking for the other one at the later time when it comes back to 0. So this one makes sense, but it's not the one we're looking for. So we're looking for the one where we're going to set this equal to 0. I didn't show it here in my solution, I guess, but set the thing in parentheses equal to 0 and solve for t. And that's a linear equation. You don't have to do any quadratic formula stuff. You get t equals 2.89 seconds. Now, once I've got that t, I can plug into the x versus t equation. And remember, in the x direction, ax is 0, so that pesky third quadratic term just goes away. In our coordinate system, x0 is also 0, so I can simply calculate x equals v0 times t. That's 16.85 times the 2.89. We now know how long in between initial and final. We just found it out. And so the solution is, it goes 48.62 meters. That's the horizontal distance that it goes, the difference between x final and x initial. All right, and that's the end of the discussion of this chapter. We need a lot more practice with these kinds of problems, but you'll get that hopefully in class and in the homework.